Yeah, so I've been completely unable to solve question 27. So I do think I have the other solutions in mind. So let me go ahead and write those down and think about 27 some more. So this is a mapping from, let me turn down the volume on the volume perhaps. T is a linear mapping from V to W, and prove that there exists phi of 1 through m such that something like this always works, right? And then since T of V lands at U and W, these phis are just coefficients that sort of move you to, like since W1 through Wn form a basis of the space that this W is in, these are sort of like control knobs that sort of dial up and down which axis gets extended longer and which is shorter. So immediately you think, well, this should be possible, right? Since W is a linear combination of these things, and these are just coefficients that you can tune for each specific V. And as a concrete example, let's say you are mapping from 1, 0 to like 1, 2, I don't know. I'm not sure what kind of linear map would do this, maybe none, but here we just want to say that this is 1 times 1, 0 plus 2 times 0, 1. Then you just want to say phi 1 of 1, 0 is equal to 1, and phi 2 is of 1, 0 is 2. Because what you're saying is when you got this 1, 0, you know, dial the coefficient so that it's 1 along the x-axis and 2 along the y-axis, because you know that it's going to end up like this 1, 2 here. So you expect that some sort of control like this is possible, but it's not clear how you will formulate such a thing. And after some trials, we've been able to deduce the best formulation I can think of, which is, I don't think I'll exceed it. So consider this. T of B1 is some linear combination of W1 through Wn. Okay, and actually let me write this in a slightly more interesting way. And this will actually directly lead into the matrices stuff that we will talk about directly. But before I even jump around to there, this is very important for establishing that intuition. Right? So T of V1 is equal to some linear combination W1 through Wn, and we call the coefficients of that linear combination A11 through A1m, just as a matter of labeling things and giving them some variable names. And same through every single element that's mapped by a basis element in V, right? And then you get a notion of things starting to like make sense now, because what will happen here is for arbitrary V in this vector space V, it can be written as a linear combination of the basis, right? And by linearity, you can just break it up like this. And this form is perfect because these are exactly what you want, right? We got TV1 through TVN, so you just substitute them in, and so on. So you all notice that, you know, the coefficients of W1 in this whole sum is really C1 times A11 plus, let's say, C2 times A21, and then etc. So if you want to write down the concrete coefficients, then what you could say is what's in front of the C1 should be C1 times A1 plus C2 times A21 plus etc. plus Cn plus, and this is going to be equal to your phi of phi1 of V, right? Because you know that V can be expressed as a linear combination of the bases. So there must exist C1, so and C1 through Cn in fact, so that this is equal to V. And once that is true, you can put those C1 through Cn in here. These are elements you already know. So this is then a way to fix such phis. And so that's quite interesting, because what these functions really are just ways of telling you that once you have what TV1 through TVN is, you have a notion of how the entire linear transformation is going to work out, and you can describe every linear combination, every single element that is in the range of T as a linear combination of those things. So those things uniquely identify such a linear combination already. So you can give me those, and they form the basis or a spanning set of range T. In fact, those elements that you are staring at will form the matrix, which will sort of become like isomorphic with a linear map. So it would be almost synonymous with a linear map in a way, because that represents all the characteristics of a linear map. If you know what A1 through A1n and A1 through, if you know what this matrix is, then you've already tuned. With this you can tune phi1, with this you can tune phi2, and you can tune every single function already. So this matrix alone is enough information to identify the linear transformation, which is why it's encoded in this way. But there's a much more elegant reason why they use a matrix, which will be shown later with some computational stuff. So yeah, this stuff makes you wonder about math, because sometimes you sit down and think, well, how did someone think of that, right? But maybe this is all quite above someone's head right now, but it was above mine a while back. So then this question, I had to look at the answer key somewhere. But the gist of it is that since you are mapping from V to F, and F is that's just your one-dimensional vector space over the field F. So you're mapping from some place that potentially has n dimensions into a place that just has one dimension. So then the range of such a mapping must have dimension 1 or 0, right? Less than or equal to 1, because this range rests within F, which makes your kernel huge, right? Your kernel is going to be basically the rest of the V, right? So it's going to be greater than or equal to n minus 1. So think about this, only like a tiny sliver of V is actually being mapped to V, mapped to F, while the rest of it is like just entirely squished down to 0. Because that F doesn't have space, right? So everything else is just got mapped to 0. There's no more space for it to map to. So then from here, you get a sense of what's going on. You can do casework, because it's just less than or equal to 1, right? There's only 2 cases to consider. One, that the range actually is just 0, and that's possible. So I'll consider that case first. So if the range of this phi is just 0, then the null space is just the entirety of V. That makes this true. That makes this bottom statement true because this is the entirety of V, while there's no elements in this set at all, right? Because there exists no U in V, which is not in the null space. With all V is in the null space. That's a more of a trivial case. And then we'll talk about the more difficult case. Considering when you have range that has dimension 1, then the dimension of the kernel has a -1, right? So what you want to do here, and you must be very careful about the way you do this, is you want to construct a basis for the range, right? All elements span the range and are linearly independent. So the basis of the range, let's say, is just one element because it's dimension 1. It's just V1. And you extend it to a full basis of the entirety of vector space V. Then those elements which are not in the basis of the range form a basis of the kernel, right? And these are linearly independent from each other. So the vector spaces they span, which are what is not in the kernel, rather V subtract the kernel, and what is in the kernel, these two sets are in fact they don't share an intersection, because if they did, then there would be a linear combination between those two parts which are equal to each other, and it's non-trivial because these are only supposed to share 0 in common. They share a non-zero element in common, and get C1E1 is equal to some non-trivial linear combination. And then this cannot happen because they were linearly independent by the fact that you extended it to the full basis, right? So then what you can say is that since they are this set V subtract kernel and kernel itself are only share 0 in common, then you can do this XOR looking thing, right? I betrayed the fact that I'm more of a computer science major than a math major. Let's call it direct sum, right? So we can perform a direct sum among those two spaces, which will then form all V, because the vector here, which forms the basis of the null space, and the vector here, which forms the basis of this null space, these two combined do form a basis of V. So that's why the direct sum of those two is V itself. It's quite sensible because any element in V can be expressed as a linear combination of the basis elements, which can then be broken down into an element of the null space and an element of not the null space. And that all is quite interesting. So in fact, this is quite a special kind of map. I think it's called a dual, perhaps. It'll come up much later in the chapter. And I think that's why they're trying to discuss it right now, so people can gain some intuition. And suppose these are linear maps from V to F that have the same null space. Then you want to show that. Let's see what this. At first, this question troubled me quite a while, as usual. Most of these later questions do. But if you think about it, right, it does make sense. So think about this, right? Since you are mapping from V1 and V1 and V2 are both mappings from V to F, and they have the same null space, right? So what is not in their null space is also the same. Right? So the elements that actually map to some non-zero number in F, all those elements are the same across V1 and V2. Then what you gotta think about is this, right? How can you establish such a constant, right? Then what you know is like, you want to probably establish a basis of this. And such a basis will only have one element, because once again that, or maybe not, actually that's wrong. It might have many elements. They get squished down into one dimension. That's possible. But whatever it is, the basis of this and this agree. So let's say that you map some arbitrary element which is inside of this space. So then it can be written as a linear combination. Let's give it a value. So let's give it a value A. Let's call phi2 map of that P. Then I claim that C is just equal to B over or A over B. And the reason why something like this would work, or perhaps I have to dive a bit deeper to explain why something like this would work. Something like this. So you know that V1 of V1 is going to get you to some V1, and V2 of V1 is going to get you to some B1, right? This is a viable, this is something that's intuitive to write down. And we try something quite similar to this. Then you might think, well, what happens if B2 over A2 is not equal to B1 over A1, right? What happens then? Oh shoot, I think. I haven't solved that yet. Yeah, originally I thought that the non-kernel part of B that maps to F must be one-dimensional, which is why everything must be that way. But this is simply not true by the looks of it. When you have multiple dimensions, this becomes a bit fishy. I think those two ratios must be equal, but I'm not sure why. Let me just skip this one for now and just go directly to question 31. Oh, this one is not too bad. If you map T1 from, let's say this is the standard basis of R5. Let's map it this way. And T2, E1 and E2 and E3 all map to 0, while E4 maps to E2 and E5 maps to E1. And T1 is not a linear multiple of T2 because, let's say T1 of 0, 0, 1, 2 is going to be equal to, let's say 1, 2. And T2 of the same thing is going to be 2, 1. These two are not scalar multiples of each other by any stretch of the imagination. So, yeah, that one's not too bad. You would think like question 30 will be perhaps easier, but it's not. Okay, no, actually, what I previously thought was correct. You can't have many dimensions mapping to the same thing. And here's the reason why. Let's say we subtract the kernel of phi1 has dimension greater than 1. Then let's say you can establish a basis of such a space, which will consist of, let's say, basis elements v1, v2 through vn, I don't know. And pick arbitrary vi and vj such that I is not equal to j. Then you know you have this linear transformation is inside of f, and so is this linear transformation, right? Then some linear combination, those will be 0. And here's the reason why. So let's say T1 will be 1 is equal to 8 in F, and T1 V2 is equal to some B in F. Then B times T1 V1 minus A times T1 V2 will be 0, right? So you can maliciously construct an element which is also supposed to be in, we subtract the kernel of phi1, but then this element is also in the kernel, so then you arrive at a contradiction, which means that the kernel must not have dimension greater than 1, which means the kernel must have dimension of, so sorry, that means the kernel, the space of v subtracting the kernel must have dimension less than or equal to 1. And this is then quite reasonable because you can first let us assume that it has dimension 0, in which case everything maps to 0, so you know that's fine because 0 times phi1 is equal to 0 times phi2 is equal to phi1 is always true because phi1 everything's in the kernel, so this is always true. Well, let us assume that you have a case where dimension is of this thing is 1. Then establish a basis of it, which is b1. Then if you have phi1 of b1 equals to a, and phi2 of b1 which is equal to b, then simply allow c equals to, simply allow, this wasn't simple, allow c equals to a over b, which will work out. And the reason is because for every element which is in this, it must be some multiple of this, and any multiple of this will, let's not use c because I already used c here. We'll have something like this, and then the ratio of those two is just c, so it does work like that. Yeah, so the only question which I've not been able to solve in this section it seems like, is 27. So that's a tough question, tough nut. I'll come back to think about it later.